We've looked at two different sampling distributions so far. We've looked at the sampling distribution for number of successes. That's the normal approximation for binomial. And we've looked at the sampling distribution for proportions. My hope is with this lesson that we'll be able to look at a sampling distribution that looks at averages. This is called the central limit theorem. I'm going to start by making sure I remember how to find an average. I'm finding x bar for the set 2, 6, 10, and 14. In order to find a sample average, I need to take all of these values, I need to add them up, and I need to divide this by the number of terms. Looks like there are 4 terms here. So when I type this into a calculator, I get an average of 8 or so. Great. That process again, though, to find the average is I took my first x value plus the second x value all the way up to my nth x value, however many of these I have. And I'll divide this by the number of terms, where n is the number of values. This will be really important for what's coming up. And here's the general setup for what we're dealing with. Suppose we are sampling from a distribution that has an average of mu and a standard deviation of sigma. How can we compare the likelihood of sample averages? For example, would it be unusual to get an average of 5 for a set of 2 dice rolls? Would an average of 5 be unusual for a set of 15 dice rolls? So in 2 dice rolls, I can get something like a 4 and a 6 averages out to a 5. But if I'm trying to get that for 15 dice rolls, I need to have considerably larger numbers consistently. That seems like that's harder to do. So it seems like the sample size is going to play a role into sort of the spread or the likelihood of some of these events. So let's calculate an expected value and a standard deviation for this x bar model. So to find the expected value or the average here, I'm going to rewrite x bar using this above information. X bar I get by adding up all of my x values, and I divide this by the number of terms. Now, in this paragraph here, I'm making the assumption that the average for each of these individual trials is some number mu. I'm also assuming that it has the same standard deviation for each of these individual trials, sigma, which is equivalent to saying the variance for each of the trials, I am assuming, will be sigma squared. So when I'm looking at the expected value of adding up a whole bunch of these things, I'm really adding up a whole bunch of these mu's. So suppose I am sampling from something that has an average of 8. I expect the first thing on average to be 8, the second thing to be 8, and so on. So I'm expecting mu for the first, mu for the second, all the way up to mu n times. And on the bottom, I have n, the number of values I'm working with. If I have mu plus mu n times, that's the same thing as saying n times mu. There are n of those mu's. I'm dividing this by n. And I can do a little bit of simplification here because I'm noticing that there's both an n on the top and the bottom. So if I cancel that n out, I'm left with mu. Here is my first of 2 results. I expect my sample average to be close to my population average. This is a fairly reasonable result, all things considered. So, for example, if I wanted to know what the average income was for Beaverton, and I sampled 600 people in Beaverton, I would expect my sample average for those 600 people to be really close to the overall population of that entire region there. I expect my sample averages to look like my population averages. In order to find the standard deviation, I'm going to first find the variance. And the variance, I'm looking at the variance of the first trial, plus the second trial, plus third trial, all the way up to the nth trial. And I'm dividing by n. The reason why I'm working with the variance is going back to my random variable rules, I had expected value rules and I had variance rules, but I didn't have nice standard deviation rules. So what I noticed in that earlier lesson was if I was looking at the variance of a whole bunch of these things added together, it was really each of those individual variances, sigma squared for the first, sigma squared for the second, all the way up to sigma squared for the last one, showing up n times. And as you can see, the variance is kind of squaring each of those values as it goes along. So when this n comes out, since it's at the variance level, it's actually an n squared. When numbers come outside of the variance, they become squared. Rewriting this a little bit, I have n of these sigma squareds over an n squared. I can do a little bit of cancellation, not a lot. Can cancel out one of the n's from the top and the bottom, and I am left with sigma squared over n. So if I want the standard deviation, that will be the square root of the variance. The square root of sigma squared is sigma. The square root of n is just the square root of n. So this says I'm expecting my sample averages to be closer mu. The amount that I'm expecting those sample averages to deviate is the sigma over the square root of n number. Putting these together into a single model, I expect that my sample averages will be normally distributed with an average of mu and a standard deviation of sigma over the square root of n. Just like I had an X model for looking at counts and a p-hat model for looking at sample success rates, I have an X-bar model to look at sample averages. I'm going to rewrite this formula on the next page. X-bar is normally distributed with a center of mu and a standard deviation of sigma over the square root of n. This is used for looking at sample averages. And as was the case for all of my other models thus far, there are three assumptions: a random sample, meaning no bias, independence between the trials, or the backup for that's the 10% rule. My last assumption has something to do with having a large sample size n. In the case of averages, that ends up being at least 30 or more samples. And as you'll see from doing some more hands-on examples through the term here, the distribution looks more and more normal as you sample more. If it started normal, though, you don't necessarily need 30 samples to be okay. So for example, if I had a distribution that I was sampling from that originally looked like this, I would consider that to be okay, sort of regardless of what that n is. That's a relatively unimodal and symmetric looking graph. Let's use this now to do just a whole bunch of examples. So that was just like 4 or 5 minutes of theory. Let's get into straight application for a while. So sample averages should have a normal distribution with an average of mu. I expect my samples to look like my population, give or take sigma over root n. Suppose that for a single die roll, the average is 3.5 and a standard deviation is 1.708. If I roll the dice 6 times, and I'm going to ignore that n is too small here, what can I expect to happen for these averages? Well, I would expect the sample average for a set of 6 dice roll to be normally distributed with a center of 3.5 and a standard deviation of 1.708 divided by the square root of my sample size, n. I'm going to type that standard deviation into a calculator and we'll see what we get. I get 0.697. So this tells me that if I were to roll a die 6 times in a row and take the average of that, I'm expecting it to kind of be in the middle at this 3.5, kind of give or take 0.697. So this means that eventually I'm expecting it to be really unlikely to get an average of, say, 6, because in this case, that would mean getting 6 sixes in a row. That's pretty unlikely. Instead of just looking at 6 samples, let's now deal with a scenario for 100 dice rolls. Physically, this is starting to get into stuff that we wouldn't actually want to do, so it's really nice to have the theory to help us out. I would expect to have an average of mu. I'm using the same formula. The only thing I'm changing here is 100, with the standard deviation of 1.708 divided by the square root of 100. Now, just a note here, one sample varies a lot. 1, 2, 3, 4, 5, and 6. Those are the things that I can get on a 6-sided die. And I'm kind of expecting each of those things equally often. If I rolled a die 100 times and I got nothing but 6, though, that's really, really unlikely. So I'm expecting things to get closer and closer to this average as I have larger samples. The way that I should see that is as my n increases, my overall standard deviation should be getting smaller. When I type this into my calculator, I've gone from a standard deviation of 0.697 to 0.1708. It has gotten considerably smaller. So for example, an average of 4.25. This feels like this should be fairly likely. It's not that far away from 3.5. But let's see what's going on if I'm considering this sort of value for 100 rolls. Well, I'll find a z-score. I'll take the value that I'm curious about. I'll subtract the center. And I'll divide this by the standard deviation. My value is 4.25. I was expecting 3.5. And I'm dividing this by the standard deviation of 0.1708. So in my calculator, I'm typing this in. I get a z-score of approximately 4.39, way more than 2 standard deviations away from the center. I would consider this to be unusual. So it is unusual to get an average of 4.25 for 100 rolls because it's more than 2 standard deviations away from the center. I want to continue using this distribution, just kind of plugging in mu, sigma, and n to test some claims. So Subway claims that their foot-long subs should be 12 inches on average. This is a claim that they're making about all of their subs, so a mu for all of the sandwiches, 12 inches, with a standard deviation also for all their sandwiches of 1 inch. Knowing this, how likely is it to get a sample average of 10.5 inches, let's say 10.5 inches or less here, for 50 samples? So I'm looking at n equals 50 samples. So suppose that someone's been going to Subway a lot. They've been getting averages of 10.5 inches or less for their subs. They've been measuring these things at home. And they're getting really frustrated because they're told it's supposed to be 12 inches long. So let's find the probability of getting 10.5 inches or less, assuming that it's really 12 inches, and they're just getting bad luck when it comes to the subs. Like they're just getting the smaller parts of the batches just due to sample variation. If that were true, then my model, since this is a question about averages, will be normally distributed with the center of mu and the standard deviation of sigma over the square root of n. My mu here is 12 inches. My standard deviation is 1 inch. And my n is 50. Typing this standard deviation in, one sub varies quite a bit. It can vary up to 1 inch, kind of give or take. But on average for 50, it should vary much less than that. So I have 0.141 or so. So I'm going to do what I always do after I have the model. I'm going to draw my picture. I'm going to calculate my z-score. And I'm going to come up with a table value. When I'm drawing my picture, my center is 12, and I'm counting by 0.141 or so. And I'm looking at 10.5 inches or less. I'm shaded to the left. This looks like a small probability. Let's kind of test that claim. My value is 10.5. The center of my curve is 12, value minus center, divided by my standard deviation is 0.141. I'm going to type this into a calculator and I'll see what I get for my z-score. And I get, whoa, negative 10.64 or so. If I try to look this up on my normal table, I see that it's off the table. So the smallest thing I have is like 0.0002, and it's even smaller. So it's probably like 0.0000, a whole bunch of zeros and then a 1. In this situation, we would call that 0 plus. So the likelihood that someone gets 10.5 inches, assuming that Subway's claim is true, is close to 0% for 50 sandwiches. In other words, I have evidence that Subway is not telling the truth when they say their sandwiches are 12 inches long. This gives me a way to kind of test to see if something is reasonable or not reasonable. So as another example that I would encourage you to kind of work through, suppose that Starbucks claims that their teas should have 20 ounces with a standard deviation of 1.2. We think the actual average is less than that. Test the claim using the framework of a hypothesis test if a sample of 100 teas yielded an average of 18 ounces. So try to go through this problem on your own here and see if it is rare or not rare. Do we think that we're being told the truth, or do we have reason to believe that we're being lied to? Let's try another one though. Suppose that the average weight of adults is normally distributed with an average of 170 pounds. So my sample average that I'm going to be comparing 180 pounds, my population average 170 pounds. So 170 pounds, okay. With the standard deviation of 30 pounds, would it be unusual for a group of 50, my n is 50, to have a sample average weight of 180 pounds? So I'm wondering, is x bar equals 180 pounds unusual? For one person, 170 pounds would not be unreasonable at all, considering weights vary considerably. It's 170 for one person, and if I'm drawing the curve out, I'm counting by 30s, so this could change quite a bit. However, I'm not looking at just one person at a time here. I'm looking at 50 people. I expect my average weights to be normally distributed for the set of 50, with the center of mu and a standard deviation of sigma over the square root of n. N stands for normal. I don't plug anything in there. I'm told that the average weight should be 170 pounds. I'm off by 10 pounds. That doesn't seem like I'm off by that much. My standard deviation is 30. And I'm looking at a sample size of 50. it varies by 30 for one person, but if I'm looking at 50 people, it varies considerably less. This is 4.243 or so. To determine if this 180 is usual or unusual, I'm going to find my z-score. I'm going to take my value that I'm concerned about, 180. I'm going to subtract the center of my curve, 170. And I'm going to divide this by the standard deviation of 4.243 or so. I'm going to type this into a calculator. Let's see what we get. I get something like 2.36. So while it's not unusual for one person to weigh 180 pounds, having an average of 50 people, randomly selected people weighing that much, is starting to get unusual. So x bar equals 180 pounds is more than 2 standard deviations away. From the center. So it would be considered unusual. Let's look at another example. So the inn at the Spanish Head has an elevator with weight capacity of 2,000 pounds. And suppose that I am in the elevator with 11 people. And I'm wondering, okay, should I be concerned about the weight capacity of what's going on with this elevator? And let's assume that the weights follow the distribution that I have above. So my concern, my question, what is the likelihood that the total weight for these 11 people is equal or greater to 2,000 pounds? This is ultimately the probability of being over the capacity. So this is the probability of danger in this situation. Labeling what I have tells me the weights have an average of 170 pounds, a standard deviation of 30 pounds, and I'm looking at 11 people here. So if I think about what's going on with the average weight distribution for people on this elevator, it should have a center of mu and a standard deviation of sigma over the square root of n. In this case, I have n, I have 170, I have 30 over the square root of n. My n is 11, and if you're worried n equals 11, this seems like this is too small of an n, because this is less than or equal to 30, and that's a bad thing. I should have a large sample to use this. Going back up to the top, though, it said the weights started normally distributed. So even though my n is less than or equal to 30, it starts normal. So I feel good even though I have a small sample size here. So weights should be normally distributed with an average of 170 and a standard deviation of 9.045%. So looking at this, I'm noticing something a little bit weird. 2,000 seems really big compared to this 170. And part of the issue is this is currently a statement about totals. So right now I'm looking at the probability that the total for 11 people is greater than or equal to 2,000 pounds. To change something about a total into an average, reminder, I find averages by taking those totals and dividing them by the number of values. So let's take this 2,000 number and let's divide that value by 11, the number of people. So I got 2,000 over 11. This gives me 181.82. Here's what this means. If each individual on average weighed 181.82 pounds, I should be concerned about being over that weight capacity because in total, I would hit the 2,000 pounds. So I'm wondering how likely is it to have 181.82 if I'm expecting 170 as the center, give or take 9.045. So I'm going to draw my picture. I'm going to find my z-score, and I'm going to look it up. Drawing my picture, I've got 170 in the center. I'm counting by about 9. I'm just coming up with a rough sketch of the graph here. And my value is 181. It looks like it's a little bit more than 1 standard deviation away. And I want that amount or more. I'm finding the size of this tail here. So to find the z-score, I'm going to take the value I care about, 181.82. I need to match things up. So this was a model for averages. This is now a question about averages. I'm subtracting the center, 170, and I'm dividing it by the standard deviation of 9.045. I'm typing this into a calculator. And I get a z-score of about 1.31 or so. So I'm going to consult my table. I'm going to go to where the 1.3 row meets the 1 column, and I see a table value of 0.9049. Notice my table is shaded to the left, but my picture here is shaded to the right. So if I want the probability of having the total weight of these people be more than 2,000 pounds, since it's shaded to the right, I'm going to want 1 minus this table value. In other words, there is a 1 minus 0.9049 is going to give me 0.0951. Putting this in terms of the context here, there is a 9.51% chance of being over the capacity. Risk analysis, whether or not you would be willing to take that sort of a chance is going to be totally dependent on the person. But you could see 9.51 and think that's too high of a probability for me to be comfortable with. I might be comfortable with a 1% chance of the whole elevator being overweight capacity, but 9.5.1% seems a bit high. Or you might be thinking it's better than a coin flip, let's go for it. But this is the process for testing these sorts of things. Again, if you happen to run into a problem that's about totals, you can change a total to an average by dividing it by the number of terms. We've now looked at 3 main models, and I want to finish this video just by doing kind of a quick comparison of those 3 models and kind of determining when you should select which one. So here's sort of my guide here. If you're studying a problem that's about sample means, and I'm going to use this model if it's dealing about totals like we just saw before. I'm also going to use this if it's involving averages. And this is one of the few models that I have that has a way of dealing with problems involving units. So these are all pretty good tips that you should be using the central limit theorem model. An x bar is normally distributed with the center of mu, and a standard deviation of sigma over the square root of n. If I'm looking at number of successes, so if I'm dealing with something that I can count, then my center is n times p, and my standard deviation is the square root of n times p times q. That was the normal approximation for binomials. Finally, if I'm dealing with something involving percentages, my p-hat model is normally distributed with the center of p and the standard deviation of the square root of PQ over N. I've got several examples below here, and I'm going to read through them, and I'm going to identify which kind of model it is, and then I'm going to answer the question that they're asking me in each. Let's take a look at 8. Would it be unusual to win $10 on average? I already know what I'm trying to find here. $10. I've got units. I have to be using this thing involving the distribution with units. Another reason, it says average. This is the model for looking at averages. So this question is going to be an X bar style question. And X bar is normally distributed with a center of mu and a standard deviation of sigma over the square root of N. My mu in this case is -2. My standard deviation in this case, they're telling me, is 40. So I'm expecting to lose $2 on average playing the game because that's how the casino makes their money. Standard deviation is $40, and I'm playing it 30 times. I'm typing that 40 over the square root of 30 into my calculator. This gives me 7.303 or so. And the question I'm trying to answer is X bar equals $10 unusual? So let's use this as our value and let's find a z-score. My z-score is going to be my value minus my center, so minus -2, divided by my standard deviation, which gives me a z-score of 7.30. This is a 3. 1.64 or so. So it would not be unusual to win $10, even though I'm anticipating losing $2. So this is within 2 standard deviations. This X bar equals 10 is considered usual. Let's do another one. Would it be unusual to win a game 6 times if you played 30 times? This feels like it's based off of counts. So I'm wondering, is it unusual if X is equal to 6? And let's take everything we know. We're playing the game 30 times. And we're told that the success rate should be 15% of the time, which means they should lose 85% of the time. Is X equals 6 unusual? Well, let me look at my models. Not about averages. It's about counts and how many times. So I can do this. I might also be able to do it as percentages if I think of the 6 out of 30 as a decimal, but let's just do it for the counts. So the model that I'm going to use to find a z-score here to see if this is usual or unusual is X is normally distributed with the center of n times p and a standard deviation of the square root of n times p times q. My n is 30. My p is 0.15. And my q is 0.85. I'm going to type this into a calculator and I'll see what I get. Now, if I actually check the assumptions on this, I would see that my n is too small because my n times p is only 4.5 here. I can still technically find the z-scores, although it would be inappropriate for me to look those z-scores up on a normal table. But I'm getting an average of 4.5, and I'm getting a standard deviation of 1.96. So I'm going to take my value that the question's about, minus the center of my model, divided by the standard deviation for my model. So all these setups are really, really similar once you have the right distribution. In this case, when I type this into my calculator, I get something like 0.77 or so. This is within 2 standard deviations, so x equals 6 is considered usual. Let's deal with another one. Would it be unusual to win 20% of the time? So is a sample success rate of 0.20 unusual? If I play the game 30 times, my n is 30, and it is known that you should win 15% of the time, my p is 15, which means I should lose 85% of the time. Looking at my options, it's not really about averages. I don't have units. I'm not doing that. I can count how many times I win, so I could use this one. But my question seems to be written about percentages, so I think it's going to be easiest to use this bottom one. I expect my sample success rate will be normally distributed with the center of p and a standard deviation of square root of pq over n. Again, I just want you to notice my question, x bar, matches up with my model x bar. My question about x matches up with my model about x. My question p hat matches up with my model of p hat. For p, I'm plugging in 0.15. I expect to win 15% of the time, so 20 seems like it might be a little bit high. Square root of 0.15, 0.85, and this is all out of 30 samples. I'm going to type this square root into my calculator. And when I do that, I get 0.065 or so. Let's find that z-score. I'm taking the value that I care about. I'm subtracting the center. And I'm dividing by the standard deviation. I'm going to type this into my calculator. And when I do this, I get 0.77. And I'm seeing that p hat equals 0.20 is usual because it's within 2 standard deviations. But I'm also noticing something else that's a little bit strange. I just got the same z-score of 0.77 twice in a row. And I'm kind of wondering what the heck is up with that. So just as a note on this last problem, if you try to do this based off of percentages instead, notice if I took this 6 and I divided it by the total of 30 to rewrite this as a problem about percentages, this actually gives me 0.20. So this is really the same question here that's been written about counts here and about percentages down here. So I'm getting pretty much the same answer for my z-scores when I compare them. In fact, I can go from this 4.5 to this 0.15 by dividing by the total number of terms, 30. Let's try that out. So in my calculator, I'm going to take 4.5. I'm going to divide it by 30. I'm taking a count, and I'm going to rewrite this thing as a percentage instead. And 4.5 over 30 gives me 0.15. There's my success rate. Great. A little hard to see my screen there. Let's look at the next one. I've got 1.956. If I divide this by 30, I get my standard deviation of 0.0652. I get my standard deviation of 0.0652 or so. So these bottom 2 models, they might look like they're different things, but they're really not. So when I say you have 3 choices of models, it's really more like you have 2 choices of models. You either have this when it's about totals and units. This is the only one that deals with mu's, sigmas, and n's. But if you have p's and q's, you actually have your choice of either one of these bottom things. They're interchangeable. How do you know which one to use? Well, if it's written more about counts, it's probably easier to use the X model. If it's written about percentages, it might be easier to use the p-hat model. But you do have options, and it gives you a way to double check your work. Okay, we kind of finished up the triplet there by looking at this X bar model, the central limit theorem. I think this is a remarkably useful distribution, and I would encourage you to practice using it.